Assalamualaikum warahmatullahi wabarakatuh. Okay, we will continue our e-learning. Okay, due to MCO problem. Okay, previously I think I already teach you about the Bernoulli equation. Bernoulli energy and equation in chapter 4. So today I just give a glance through before we continue to other subtopic. Okay. Okay. Okay, in this chapter we will learn about conservation of mass, continuity equation, mechanical energy, efficiency, Bernoulli equation, general energy equation, energy analysis and steady flow. Okay, so this is a few topics that we will cover in this topic. Okay. Okay, there is three types of open system, which is first is open system, as I mentioned previously in class, that open system is a system that can exchange both. Mass can exchange, energy also can exchange with an outside system, so such as your body system. So another one is closed system. For closed system is the exchange energy but no mass with an outside system. So is a typical portion of larger system which complete contact, such as for example our Earth. We absorb a lot of energy from the sun, but the exchange of matter with outsides is almost zero. Okay, the third one is isolated system. Okay, the isolated system is can exchange neither energy nor mass with outside system. Okay, for example, we have a thermos, closed bottle. For example, there is no leaking or is insulation effects which help to isolate all the energy, even a mass, maintain and remain inside. Okay, one more thing, heat can be transferred between open system and between closed system, but it cannot be transferred in isolated system. So heat, it can be transferred from open system and closed system, but in isolated system it cannot be transferred. That's why this concept people use to for the usage of thermos bottles and to remain the heat inside of the system. Okay. Okay, this is several example of open systems. Okay, so open system also we call as a control volume, which is a properly selected region in space. Okay, so usually it encloses a device that involve mass such as compressor, so turbine and nozzles, and both mass and energy can cross the boundary of the control volume. Okay, you can see here, this is the one of example of open system. Okay, example of open system. So we have one inlet, so this is the inlet. Okay, then we have one outlet. Okay, when the inlet come in, and there is a water heater here, so this is a water heater. So the fluid, the water will be remains and inside of this water heater before it's going out for supply. So if you can see here, this area, okay, this area, okay, this area, the dotted line, we call it as a control surface. So this is our surface that we will study on, or for example in terms of the heat, in terms of the temperature and something. So this one is the control surface. Okay, you can see the second example, which is control volume with real imaginary boundaries. Okay, so this is the control volume of a nozzle. Okay, so this is the boundary, this is the real ni. So we can create one of imaginary boundary here. You can see the dotted line. This is imaginary. So any calculation, any findings, we need to have our control surface and control volume. If we don't do this, it's very difficult for us to focus in which area. Okay, the second B example, we can see there is a control volume with fixed and moving boundary. This is some examples such as pistons. Okay, so this is the fixed boundary. Okay, dotted is a fixed boundary, but in the same case for the pistons, these pistons start to move, going downward, then the boundary will be moving. So the boundary can be compressed and moving. This is the example of an open system which need a control volume and also a control surface. Okay. Okay. One more thing is the important concept that you need to understand is all about the conservation of three things. The first is conservation of mass. Okay, conservation of mass, which said that mass cannot be created, nor or destroyed, and it only can be rearranged. Mass can be rearranged. The second is conservation of momentum. Okay, momentum conservation said that the total linear or angular momentum in isolated system is constant. So it remain constant. Okay, for isolated system it remain constant provided there is no external force is applied. If there is no external force, the momentum will be remain the same. But if we put external force, it will be changed lah. Same like mass, previously mass cannot be created, but it can be rearranged. And the third one is conservation of energy. So the conservation said that the total energy in the system constant. Okay, the energy will be constant, so it cannot be created nor destroyed. However, it can transform from one to another. So the energy can be transferred. This is transformed from kinetic energy to potential energy, but it cannot be created. Okay, and also destroyed. So this is the three conservation of mass, momentum, and energy. Okay. Okay. We go for detail for conservation mass. Okay, conservation mass is one of the most fundamental principle of nature. Okay, we know that it's very important. Everything's most of the sciences start from the concept of conservation mass. So conservation of mass is conserve property, and it cannot be created or destroyed, like I said previously, during the process. However, mass and energy can be converted. So it can be converted from one situation to another situation. So this is based on one of the popular scientists is Albert Einstein. So from Albert Einstein's, I think you are familiar with this equation, which is E equal to mc square. E is energy is equal to mass times c. C is the speed of light. Speed of light in a vacuum, which is c equal to 2.9979 times 10 power of 8 meter per second. Okay. Okay. Okay, next we focus on mass and volume flow rate. What is the difference of mass and volume flow rate? What is the equation that need to be understood and also need to be mastered in order to use it. Okay, mass flow rate. Okay, mass flow rate is, the formula is normally MS flow rate is m dot. Okay, we call it m dot. So you can see here m dot. Okay, m dot. M. So this is the m dot. Okay. Okay. The formula is m dot is rho VA. Okay. The rho is the density. Okay. Okay, which is V is average velocity. And A is area. Okay, this is the formula of mass flow rate, which is m dot is equal rho VA. So the most important thing, the unit is kg per second. Okay, so this is mass flow rates. So another one is volume flow rates. Okay, volume flow rate is an integration of velocity and area. So means that V dot is equal to VA. So we have velocity and also we have area. Okay, so combination of these two, there is a relationship, which is we know that m dot is equal to rho VA, and previously we know V dot is rho VA, thus V dot is VA. So if we change VA with the V dot, so what we get is we will get m dot is equal to rho V dot. Okay. Okay. So this also know that can be simplified to be V dot divided by V, which is a, in this case, the small v, we call it as a specific volume. Okay, it's a specific volume. Okay, this is the relationship between mass and also volume flow rate. Okay, so this is an example in this control volume. So there will be a average velocity, or V dot is equal to VA. So this relationship is analogous to m equal to rho V dot, or equal rho V dot over small v, which is the specific volume, which is a relation between the mass and volume in a fluid container. Okay, the conservation of mass principle for a control volume can be expressed as the net of transfer to or from a control volume during a time interval of delta t is equal to the net changes, increase or decrease, in the total mass within the control volume during delta t. So means that a total mass entering in control volume minus total mass leaving in control volume, you will get net change of mass within control volume. Means that m in minus m out, you will get delta mcv. So mass in minus mass out, you will get the difference. So this is the conservation of mass principle. This is also known as a continuity equation. Okay, we also know this concept is m in minus m out equal to delta m control volume, is also known as a continuity equation. Or we can say that m control delta m control volume is equal to m final minus m initial. Okay, so which is the mass control volume during the dose process. Okay, one thing is from this equation for the first equation and the second equation is often referred as a mass balance. Okay, we call it as a mass balance and are applicable to any control volume undergoing kind of process. So m in minus m out is equal to the rate of change of mass. Okay, even mass flow rate or even a mass. Okay, for example, the first one is the mass, the second one is mass flow rates. So this is a kg, this is a kg per second. So the concept is the same as m in minus m out is equal to delta m CV. Okay, we go for the next. Okay, this is a simple example that, for example, bathtub. For example, here we have a bathtub. So the mass in is calculated, is given 50 kilogram. Okay, so the mass out is 30 kilogram. Based on the previous slide, we know that m in minus m out is equal to delta m CV. So in this case, our m in is 50 kilogram. So when we minus with our m out is 30 kilogram, so automatically we know the remain inside of the bathtub should be the balance, which is 20 kilogram. So the conservation of mass, there is no losses of mass, but it's just transferred from inlet to outlet. For example, I have m in is 50 kilogram and outside m out is 50 kilogram, means there is no delta MCV. Okay, for continuity equation, continuity equation is from conservation of mass principle, which is have been mentioned previously. It's related with the total mass entering in the control volume at certain duration minus total mass leaving in the control volume during the same duration. So it's equal to the net of change in mass within the control volume during the same time. So means that m in minus m out is equal to delta m CV. Okay, so in terms of the definition is the net of mass transfer to or from a control volume during a time interval of delta t is equal to the net change, increase or decrease, in the total mass within the control volume. Okay, so it's similar like previously in conservation of mass, which is m in minus m out is equal to delta m CV. This is for mass. For example, for mass flow rate, m dot in minus m dot out equal to the differentiation of MCV in terms of the time. Okay, so this is a rate of change within the control volume. Okay, this is for example. So we have one control volume, which is your M1 is 2 kg per second, and M2 is 3 kg per second. So at the end, both of it, the inlet will have a one outlet, so it will come out at M3. So from here, we know the concept of continuity equation is M in summation of M dot in equal to summation of M dot out. Means that we assume that there is no losses, there is no leakage, for example. So what in should be out, so the net of change should be 0. So that's why summation of M in should be summation of M dot out. Means what in should be everything goes out. So here you can see M1 M dot 1 plus M dot 2. Okay, M dot 2 should be M dot 1 plus M dot 2. Okay, 1 plus 2 should be similar or equal to M dot 3, which is your out. So here will be 2 kg per second, 2 kg per second plus 3 kg per second should be equal to 5